Alrighty, part 2 on 11.8 on power series. We're doing radius and intervals of convergence. And in the last video, I went through two examples, and I happened to mention that there were three possibilities. Okay, the three possibilities are that the power series that you are given converges at a finite interval. Okay, and we saw two of those in the last video, right? Converges at on a finite interval, and then you check the endpoints. The other possibilities are that it converges at a point, okay, meaning right at the center of the interval, and any to the right or to the left, wherever that power series is centered, it's not going to converge anywhere besides that one point. Or there's the third possibility that it just converges everywhere, and we'll actually see a couple of those as well. But I wanted to go ahead and remind you that, and there's actually, I think, even a theorem in your book that states that sort of formally. But basically, it should just make intuitive sense, right? And it should make even more intuitive sense once we actually see it, because it has everything to do with the limit that the ratio test spits out. If the ratio test spits out something that is always less than 1, its absolute value is always less than 1, then it converges everywhere. If it's never, except where you can plug in to make 0, if it's never less than 1, then it only converges at a point. And if it's sort of conditional based upon an interval, then obviously it's a finite one, okay? And I'll discuss it a little bit more as we see examples of that, okay? And when you plug in n plus 1 into 2n plus 1, remember you have to distribute the 2 across the n plus 1, and then you'll have a 2 that'll combine with this 1, so it winds up being 2n plus 3. And this one winds up being n plus 1 factorial. And you don't actually have to do this right here. I'm just doing it so that you see it explicitly, okay? 2n plus 3, all of that over n plus 1 factorial times n factorial over x 2n plus 1. Now let's go ahead and do some canceling. I know that this is n plus 1 times n factorial. The n factorials cancel. This is 2 more than this. So if this cancels out, this is left as x squared. Okay? Well, as n goes to infinity, okay, what happens to this ratio? Well, as it goes to infinity, I don't care what x is. If n goes off to infinity, that becomes 0. So when is 0? When is the absolute value of 0 less than 1? Always, right? It's always less than 1. And this is an example of, it depends whether what classification of intervals you have depends upon what gets spit out of your limit, right? And if this gets spit out, that's always less than 1, then your interval of convergence is negative infinity to infinity. And as far as I'm concerned, it really doesn't matter to discuss the radius of convergence. I mean, your radius is infinity, I guess, if you can actually describe it as that. Okay. Well, let's go ahead and let's move on and let's do another example. Okay, n is equal to 0 to infinity of n factorial x minus 4 to the n. And a sub n plus 1 is going to be n plus 1 factorial x minus 4 to the n plus 1. Now, the fact that it's x minus 4 means that the center of this is a power series, and it's what's called centered at 4, meaning 4 is the value that gives you a 0, okay? And that shouldn't, I mean, it's the same kind of logic as the transformations and the horizontal phase shift and stuff like that. It's what makes it 0. 4 makes it 0. Okay, so 4 is the center. So at the limit, as n goes off to infinity, and notice that this isn't a ratio, so we're just going to go ahead and plop it in like this. Okay, and that gives us, once we actually do a little bit of simplification, that factorial crosses out with that. All of these cross out with all but one of those. And what happens as n goes to infinity? Well, that limit's infinity. When is that going to be less than 1? Okay? Never, 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 except at the one point right here at 4. Okay? So basically, this is a power series that converges at a point. Remember, the three possibilities are converges at a point, meaning the point at which the power series is centered. So x is equal to 4 is your interval of convergence, if you can actually call that an interval. It's at a finite, on a finite interval, which we saw in both of the examples in the last video, or it's infinite, like it is here. And it has everything to do with what does the expression look like? What is the answer to this limit as n approaches infinity? Okay? If it's always less than 1, it's an infinite one. If it's never less than 1, then it's at that one point. Okay? And if it's conditionally less than 1, then you have to work out that finite interval and check the endpoints based upon the numerical series for plugging in those endpoints into the original power series. Okay, well, let's just keep doing some examples until we sort of run out of time. Okay, how about, oh, that's ugly. Actually, n is equal to 1 to infinity of x plus pi to the n over the square root of n. Okay, well, that's not fun because obviously this thing is centered at negative pi. But let's go ahead and figure out the a sub n plus 1, and we have x plus pi to the n plus 1 over root n plus 1. So our limit, using the ratio test, is x plus pi to the n plus 1 over root n plus 1 times root n over x plus pi to the n. Now they just put in obnoxious numbers like this into some problems, largely because they want to see whether you're going to get distracted and lose your nerve. Just because the center is at negative pi, that's no reason to lose your nerve. Let's go ahead and simplify this. This cancels out with all but one of those. And we can basically kind of regroup the factors so that it makes a little bit more sense to us. Right? So we have root n over root n plus 1 times x plus pi. And when I take the limit as n approaches infinity, this ratio right here goes to 1. And what I'm left with is x plus pi, and I need to know when that is less than 1. Well, that's not really that difficult to figure out. That's going to be less than 1 when negative 1 to x plus pi, when x plus pi is between negative 1 and 1. Or negative 1 minus pi and 1 minus pi. Well, unfortunately, I now have to check my endpoints, okay? And checking the endpoints really isn't that big of a deal because when you plug in negative 1 minus pi, obviously the pi is going to cancel out, right? So if you plug in negative 1 minus pi, you're going to get negative 1 to the n over root n. And over here, you're going to wind up getting the 1 minus pi. The pi's still cancel, and you're left with 1 to the n over root n. Well, here's the thing. This right here, by alternating series, is going to converge. This is basically a p-series because it's non-alternating. This diverges. And therefore, I'm going to be convergent on the left-hand side of that interval and divergent, meaning non-inclusive, on the right hand. That is my interval of convergence. And despite the fact that pi, or negative pi, is the center right here, what was your radius of convergence? There was no denominator right here to alter that radius of convergence. That radius of convergence is just 1, okay? And so your radius of convergence is just 1. And that on assignments like this is largely all you're going to be asked for. Now, obviously, things like this wind up getting folded in and becoming a small part of what becomes a much larger problem. But in these 3 examples, we've walked through the 3 possibilities. Infinite, finite being a point, and finite being an actual interval, but not spanning off to infinity in either direction. Okay? Let's go ahead and let's just, like I said before, let's continue doing problems until we run out of time. We're at about 10.5 minutes right now. Okay, how about, okay, that'll be fun. X plus 1 to the 2n over 9 to the n. Okay, well, a sub n plus 1 is going to be x plus 1 to the 2n plus 2, right? Because you have to distribute the 2 across the n plus 1 that you're plugging in for the n, and 9 to the n plus 1. So we want to do the limit as n approaches infinity of x plus 1 to the 2n plus 2, all that over 9 to the n plus 1, 9 to the n over x plus 1 to the 2n. Okay. Now, this one winds up being, a little bit trickier. That one cancels out with all but that one. That one basically winds up making that x plus 1 squared. Okay. So what happens here is we can actually sort of represent this. This winds up being x plus 1 over 3 squared, right? Because basically all the n's have fallen out. And you need to know when is that going to be less than 1. Well, the absolute value bars are, of course, redundant at this point because it's being squared. If it's squared, it's always non-negative. And therefore, you can go ahead and say, well, if that's x plus 1 over 3 squared, that's going to be less than 1. Okay. That winds up, when you take the square root, right? Well, here's the thing. Well, let's just go ahead and keep going. So we have negative 3, x plus 1 to 3. And therefore we have negative 4, x to 2. Okay. Now, we know that x can be negative 4, right? X can be negative 4 in order for it to be less than 1. Okay? Or it can be negative in order for this to be true right here. Okay? So let's go ahead and check the endpoints right here, and we'll see what that gives us. So we have sigma, n is equal to 0 to infinity. Let's plug in negative 4, winds up being negative 3 to the 2n over 9 to the n. Well, here's the thing. That's squared, right? And therefore, this just winds up being n is equal to infinity of 1. Well, that's certainly divergent, okay? Let's go ahead and plug in 2, and you get 3 to the 2n over 9 to the n. That winds up being exactly the same thing, 1, and therefore you have also divergent. That right there is your interval, okay? What is your radius? Well, the radius is 3, right? The radius comes from this step right here. It's being centered at negative 1. So if you sort of compensate for the centering by adding 1 to it, right? How far does it go in either direction? It goes 3 to the right and it goes 3 to the left, okay? And therefore, this right here is our interval of convergence. This right here is our radius of convergence, okay? And our radius of convergence is equal to 3. Well, that doesn't wind up being too bad. Okay, let's go ahead. Let's go ahead and call it quits. I think what we've done here is I've given you an example of all of the different styles and types that you're going to run into, whether it converges at a point, converges at a finite interval, converges at an infinite interval. Um, so I'm hoping that puts you in good stead for the test that's coming up. We'll obviously sort of investigate this further as we get on into AP review and start really focusing on the way in which the AP test writers ask questions that are relevant to this skill set that we've discussed in 11.8, finding the radius and the intervals of convergence. Okay. As always, if you have any questions, please do email me. Bye.